All right, ladies and gentlemen, we are back going to continue our conversation with Newton and understands Newton's laws of motion and his law of gravity. Now, before we get into that, however, there are some terms used with Newton's laws. Now, guys, these terms are going to be used through the rest of the semester, so make sure you understand what these terms are. Now, I'm not going to go into a lot of detail because this lecture is being taped and you can re-listen to it over and over again. You've got the PowerPoints to see what's going on. If you have questions, you can still come into my office hours. You guys are still allowed to come to campus for that. You just can't come into a packed classroom. So if you've got questions, either office hours or you can email me. Remember, via Canvas, okay? All right, so let's get started. First thing we're going to talk about is velocity. People get velocity and speed confused. They're actually not the same thing. If I'm going down the highway towards Ocala, and I didn't tell you I was going to Ocala, I just said, hey, I'm going down the highway and I'm going 75 miles an hour. 75 miles an hour is not a velocity. That is my speed, okay? If I tell you I'm going 60 miles an hour, again, that's speed. What is velocity? Velocity has speed and direction put together, okay? Speed and direction, that's what velocity is. So if I tell you I'm going down the highway at 75 miles an hour due south, that is a velocity because I told you my speed and my direction. If I tell you I'm in a rocket ship going 2,000 miles an hour at 45 degrees above the horizontal, that is a velocity. I gave you speed and a direction. Direction doesn't always have to be north, south, east, or west. It could be an angle above something else, okay? There's a lot of ways of looking at direction, but keep in mind, because we're going to be using this term velocity a lot, it deals with speed and direction put together, okay? Now, what is acceleration? This is another term people constantly get confused about. First off, before we talk about acceleration, this idea that people say it's decelerating, there's no such thing as deceleration. That's some term somebody made up, and I don't know who it was, but that term doesn't exist. The only thing that exists is acceleration. So what is acceleration? Acceleration is any change in velocity. Any change in velocity. That's the basics of what acceleration is. Now remember, velocity is made up of two things, speed and direction. And so acceleration is any change in velocity, okay? So if I'm going down the highway due south, and I'm going 75 miles an hour down the highway due south, that's the velocity because I've included both things. And I slow down from 75 miles an hour to 60 miles an hour, still due south, I have accelerated because I have made a change to my velocity. And the change in this case was to speed. Now everybody thinks, well, no, Professor, wait, you slowed down. That's deceleration. Deceleration does not exist. It's not a term. If I slowed down, still going due south, I have accelerated. My acceleration, when you look at the numbers, will be a negative number. That fact that it's a negative number is telling me I'm slowing down. There's no such thing as deceleration. If I'm going down the highway at 75 miles an hour due south and I speed up to 100 miles an hour due south, that's still an acceleration. I have changed my speed. Now, I'm going down the highway at 75 miles an hour due south. I now turn and I'm going 75 miles an hour due east. That is still an acceleration, ladies and gentlemen. Did I change my speed? No, but I changed my direction. I can't beat this in your heads enough. Acceleration is any change in velocity. And why am I getting excited about this? Because students consistently miss this on a test when they sit there and tell me that when I change directions and maintain my speed, I haven't accelerated. I have. Okay? Now, in order to make sure you understand this concept of acceleration, here I have a racetrack. It's a circular racetrack. On the racetrack, I have my race car. This is my race car. My race car is going at a speed of 75 miles per hour around the track. The speed is not changing. So if you were in here, I would ask you the question. This car is going around this racetrack at 75 miles an hour. The speed isn't changing. Is it accelerating? And so I'm asking you, is it accelerating? Oh, Professor, yes. Oh, Professor, no. For those of you that said no, you missed it. Because is its direction changing when it's going around this circle? The answer to that is yes. Its direction is consistently changing. So therefore, a car going on a circular path at the same speed is still accelerating because the direction is changing. Do you all understand this? If not, re-listen to this over and over again until you do, okay? All right, so that's acceleration. So we've talked about velocity, acceleration. What is mass? This is another one of those concepts. People get confused all the time. They say mass and weight is the same thing. They are not the same thing. Mass and weight are mathematically directly related to each other. Directly related, but they're not the same thing. Mass, and this is a really good definition, is a measure of the total amount of material inside of an object. So, ladies and gentlemen, you have mass because you are made up of material and you exist. If you exist, you have mass. If you have mass, you're made up of stuff. What are we made up of? Atoms. So really kind of what is mass? How many atoms make us up? The chair you're sitting in has mass. It's made up of a certain amount of atoms. Okay? So mass is a measure. In other words, how many atoms are inside of you, the chair, the building, whatever it is you're looking at. Okay? That's what mass is. How much stuff is something made up of? All right? To rephrase it. Now weight. Let's talk about weight. Weight and mass are not the same. The first thing I want you to understand and see and realize, I'm going to put this in red. Weight is a force. Right there. Weight is a force. Take out the, put a. Weight is a force. You must understand that. Weight is a force. Okay? So, what is weight? Weight is the force with which a body, what's a body? It's you, the chair, a car, the tables I have up here. So weight is the force with which a body presses down on the surface of the earth, the moon, Mars, whatever it's setting on. So, we live here on the earth. Your weight is the force that you are exerting on the surface of the earth. For your chair, it's the weight, it's the force that the chair is exerting on the surface of the earth. For your car, it's the force that your car is exerting on the surface of the earth. You notice my hands keep going down. What direction does weight work? It works downward only. Presses down, only in that direction. Not up, not sideways, not at some crazy angle, down. Okay? Why only down? Because weight, the concept of weight, yes, it's tied to mass. It's also tied to gravity. Which direction does gravity go? Gravity only works in the down direction. Okay? So let's put this together mathematically so you can understand what's going on here. So weight, W, which is a force, is equal to the mass of the object that you're looking at. You, a car, a chair, doesn't matter. Whatever mass of the object is you're looking at, times this concept little g. What is little g? Little g is the acceleration due to gravity. Gravity only works downwards, so the acceleration due to gravity works down. Okay? So little g is equal to the acceleration due to gravity. Gravity goes down, acceleration due to gravity only goes down. This is why weight always pushes down on the surface of the object that you're on, the Earth, the Moon, Mars, whatever it may be. Okay? You guys have simply got to remember this weight is a force. Weight is a force, okay? Why do I keep hammering this? Because we're going to talk about force later on here, okay? And they are one and the same thing. Okay, kinetic energy. What is kinetic energy? Kinetic energy is the energy of an object as a result of its motion. So in other words, if an object is in motion, it inherently has something that we call kinetic energy, all right? So what is kinetic energy? We're going to look at it mathematically. Kinetic energy, Ke, that's how we define it in basic physics. Ke, kinetic energy, is equal to, this is the mathematical equation for it, 1/2 times the mass of the object you're looking at times the velocity of that object squared, times the velocity of the object squared. If an object has velocity, it has speed and direction, which means it's not zero. It is actually a number, okay? So, remember we said that kinetic energy was the energy an object has because it's in motion. That B is showing you the object is in motion. If it's not moving, does it have velocity? No, therefore it would have no kinetic energy because I would have 0 times all this. All right, so it would be 0. So kinetic energy is the energy an object has because it is in motion. It's moving. If it's moving, it has a velocity. Okay? Potential energy. Potential energy is the energy of an object as a result of its location in space. Okay? So potential energy is the energy stored inside of an object as a result of its location in space. This has nothing to do with motion. This just has to do with the fact that this object exists somewhere in the universe and has a position. Now, we're going to look at a very specific kind of potential energy to help you understand it, okay? This is going to be kind of what I like to call gravitational potential energy, because objects in a gravitational field will have a potential energy because they are located inside of a gravitational field. They don't have to be moving. They just have to have a position in that field. Now, what is that equal to mathematically? Potential energy, PE, potential energy, this is again how we define it in basic physics, is equal to the mass of the object, whatever that object is you're looking at, times the acceleration due to gravity. Remember I told you, this is an object inside of a gravitational field, so it will be being accelerated because of that gravitational field. So the mass of the object times the acceleration due to gravity times h. H is its position in the gravitational field. Okay? So, most of the time the mass of the object doesn't change, the gravitational field doesn't change. H, its position within that gravitational field will change. So, if the object we're looking at is my pen here, now let's change that. Let's make it an eraser because I'm going to drop it and I don't want it to break. All right, well, I can't find an eraser, so we're going to use this pen that if I drop it, it ain't going to break, okay? So here I have a dry erase marker. This is my object. It is a certain height above the earth, okay? And so we could calculate the potential energy it has at this position above the earth. It has a mass, which we could measure. It's being accelerated down because of gravity, and we know what the position is, the h. So as I drop it, it's going to fall. Now it's all the way down there. It's on the surface of the earth. Therefore, the h is 0. So now it no longer has a potential energy inside this gravitational field. Okay? Now, if I have my object here, it's at this height, and I move it up to a higher height, it has more potential energy here than it did here because my height increased. If I have started here, I know what the height is, and I lower it to here. The height is less than here, therefore it has less potential energy. So potential energy is the energy that an object inherently has stored in it because it has a position somewhere in the universe. And here inside of a gravitational field, it has potential energy stored in it because it is a certain height above the object that's producing the gravitational field. Okay? Angular momentum. Before we talk about angular momentum, we have to talk about something we call linear momentum, normal momentum. Momentum is a measure of an object's resistance to change in its motion. Momentum is a measure of an object's resistance to change in its motion. So, if my dry erase marker here is in motion going straight across, it wants to keep going straight across. It will resist any change in its motion to bring it up, to bring it down, to bring it towards the board, to bring it towards you. It will resist this change in its straight line motion. Okay? And we can measure how much resistance it will put up because, again, guys, it's a mathematical equation. Now, what I'm talking about here is linear. We're trying to get to angular. This is linear momentum. We're going to lead up to angular momentum here, okay? So, what is linear momentum that we're talking about right now? Linear momentum. Again, it's that resistance to change in motion, but what is it mathematically? How do we come up with a number for that? P. I know that was called period before for Kepler. In physics, P represents momentum. So momentum is equal to the mass of the object you're looking at times its velocity. Okay? No, this is not kinetic energy. Remember, kinetic energy was 1/2 times the mass times the velocity squared. I don't have the 1/2 and I don't have the squared. So the momentum an object will have is based on its motion, its speed, times its mass. And that will give you how much resistance an object will put forward to a change, okay, in its motion. Now, angular momentum. What is angular momentum? Angular momentum means we're either we're rotating or we're revolving, one of the two. If you're rotating, you're going through an angular motion. If you're revolving, you're going through an angular motion, okay? So angular momentum is an object's resistance to change in its angular motion. If an object is rotating around its axis at a certain speed, it wants to keep doing that, and it will resist any change to that rotational motion, slowing it down or speeding it up. It will resist that. Now, if we're talking about a revolution problem, here we have, let's say, a planet going around the sun, okay? This planet wants to stay in the orbit that it's in, and it will resist any change to slowing that orbital speed down. It will resist any change to speeding up that orbital speed, and it will also resist any change that will try and take it out of its orbit. It will resist these changes. So this is what angular momentum is. Now, what is angular momentum? Mathematically, angular, there we go, momentum. Big L denotes angular momentum is equal to the mass of the object times the velocity of the object. Well, that's the same as linear. Well, it's tied to linear. The difference is it's an angular motion, not a linear. So in order to make it angular, we have to toss in this value we call R. What is R? R is the radius of rotation or the radius of revolution. Okay? So, if we are talking about an object, and let's take the Earth, because it's an object and it rotates. Oops. If we're talking about the Earth, remember it rotates around its axis of rotation. Here's the center of the Earth. That is R. The distance from the center of the Earth to the surface of the Earth, that is R. And that's what R represents in that equation. If we are talking about the Earth going around the sun, here's the sun, here's the Earth. R is the distance from the sun to the Earth. Okay, so Either way, r is a distance, but it's representing from the center of either rotation or revolution. Okay, that's what it is. All right, these terms are used in Newton's laws, okay? Certain things I will now tell you about these terms. These are things I think you probably should have learned in high school, but I don't trust that. You should have learned it also in junior high, but again, I don't trust that. Energy, whether it's kinetic or potential, is always conserved. You cannot create or destroy energy. All you can do is change its form. When we're talking about kinetic and potential energy, I can take kinetic energy and turn it into potential. I can take potential energy and turn it into kinetic. But I'm not destroying either one. I'm just changing their form. The amount of energy stays the same. You're just changing its form. It's what we call conservation of energy. Momentum is the same thing. You cannot create or destroy momentum. It must be conserved. So the momentum before an event must be equal to the momentum after an event. And this event could be a collision between cars. It could be a bat hitting a baseball. All those deal with momentum. And you cannot change the momentum. You can change the form of the momentum. Okay? And so one example they always give is the skater when they're talking about angular momentum. When the skater's arms are close in like this or like this, however you want to look at it, r is the distance from the center of the chest out to where the arms are, okay? And in this configuration, the skater's going to be spinning very, very fast. Now, if the skater now brings her arms out like this, r now goes from here to the end of the hands. R is now bigger. If r becomes bigger, the angular speed, the speed must go down. So here I have a small r and a high velocity. Here I have a large r and a small velocity. You calculate these out, the angular momentum will be the same for both. So what's the event? The changing of the arms. Okay? Changing r, changing v. The numbers, when you come up with L, the angular momentum will be the same. They may not look like it because the skater's changing speed, but the skater's also changing r. It keeps the momentum the same, even though it doesn't look like it. Momentum is conserved just like energy is conserved. You cannot create or destroy either one. You can only change the form. Obviously, my keyboard here, guys, is acting up again. Okay, so let me get this reset back up. We are now getting ready to discuss Newton's actual 3 laws of motion. Before we do that, let's take a break. Okay, I'll be back.